All right. Hopefully, you've had an opportunity to play around with the Jupyter Notebook and the K-means demos and gotten a sense on your own of how the algorithm works. In the final part of today's material, we're going to be examining a second clustering algorithm beyond K-means. And this algorithm is actually kind of a class of algorithms that take a slightly different approach to the clustering problem. So the motivation for this class of divisive clustering algorithms is that often data has structure at multiple levels. So there are different groupings and then groupings inside groupings. And we need to differentiate the data in this kind of order. So to take an example, suppose that we just have a massive class of all software that exists in the world, and we want to cluster it into some kind of structure of different types of software. So basically, we want to make some kind of taxonomy, in a sense, of software. So we may start by thinking about the different larger groupings, the top level groupings. So the main idea behind divisive clustering algorithms is that you can start by breaking the overall space into a small number of clusters. For example, all software can be broken into Amazon, Google, and Microsoft. You may be able to think of a few others, but bear with the example. And then now you have each of these clusters and you want to break those into some clusters. So then within the space of all Amazon accounts, you might want to subdivide it into products that are produced by Amazon, products that are produced by Google, and products that are produced by Microsoft. And then you could continue breaking down, for instance, Microsoft Office into the component parts of Microsoft Office. So another way of thinking about this kind of clustering is that you're trying to make a hierarchy. And there's some clustering at each level of this hierarchy. Okay, so this is a specific type of hierarchical clustering. And we might define the divisive clustering approach as an approach to clustering that creates hierarchies starting from the top and moving down. And this is a little outside the scope of the lesson, but you can contrast this with a family of approaches that start with just completely spread out data and then clump local things together in increasingly large clusters until you end up with a cluster at the top that includes everything. So you can sort of think of hierarchical clustering proceeding from the top down or the bottom up, and divisive clustering is the kind that starts by splitting the space and then splitting the parts of that. Okay. So there are a few knobs that we can turn and think about within this family of divisive clustering approaches. So one thing is that you need to rerun clustering at each level, but the algorithm you use to do that is up to you. Then you need to decide how many clusters you want at each level. So maybe you want to start with only 2 at each level and keep that exactly the same. So you're just splitting and then splitting and then splitting. Or you might want to, have more clusters at the top and fewer at the bottom, and so on. And then when do you stop? Do you just stop based on a certain fixed number of levels? Say I only want 3 levels of my hierarchy. Do you stop once you sort of hit a certain number of elements in a cluster, or do you just keep running this until you end up with a set of clusters at the very bottom of the hierarchy that contain only one element? So that's kind of the logical endpoint of this algorithm. Okay, so this is a pretty large family of approaches. Obviously, there are a lot of choices you can make for each of those decision points. But we're going to talk about a particular divisive clustering algorithm called recursive k-means clustering, which essentially uses k-means clustering, as you learned about in the previous video, at every single level of this splitting. Okay, so the idea is that at the very top level, you use k-means to create a certain fixed number of clusters. And then within each of those clusters, you kind of ignore everything else and then run k-means again. And then within each of those clusters, you ignore everything else and run k-means again, and so on until you want to stop. And by the way, this has a property which is quite common in computer science that you'll see popping up in a lot of places, called recursion, which is essentially repeating the same operation nested within itself. So you can sort of think of a recursive k-means algorithm that essentially calls a recursive k-means algorithm inside your program. But that's kind of a side note. That's more of general kind of fun thing to note. All right, so how does this look in practice? Well, let's take a concrete example. So suppose you have the collection of all Wikipedia articles. That's a lot of articles. So you want to do this in splits of 2. So say that you group all these articles in and discover the 2 maximally dissimilar clusters. Now, basically, suppose that all of those articles of people on Wikipedia turn out to divide basically into what appears to be athletes and non-athletes. This is sort of the maximally distinctive clustering cut you can make. Now you recurse. You repeat within the group of athletes, you can subdivide, and maybe you come up with basketball players and soccer and ice hockey players. And similarly, you recurse within non-athletes, and you come up with these different clusters. And of course, to be clear, these labels aren't in the data themselves. This is sort of what might happen if you eyeball the kinds of clusters you get out and look at a couple examples of the articles in each cluster. So this is kind of like us interpreting the clusters that are found rather than something that the algorithm itself labels for us. Okay. So this is a really powerful technique and allows you to find not just flat structure, but actually deep structure. So taxonomic structure that allows you to see finer and coarser levels of granularity in your data. So just to recap all the unsupervised learning approaches we've talked about, we started by contrasting the supervised learning approaches that you've been learning about with a separate family of approaches called unsupervised learning. So this is what happens when you have unlabeled examples and just find bottom-up structure among those examples without explicitly training with a ground truth output, desired output. And one particular type of unsupervised learning that's related to classification is clustering, where we attempt to group examples into clusters, a discrete number of clusters, based on the similarities in that feature space. So this is trying to find bottom-up structure in certain sets of classes. And then we looked at one particular algorithm to do that, called k-means clustering, where you specify a certain number of clusters you want, and then do this iterative alternating between moving cluster centroids around and then assigning points to those centroids and then reassigning the centroids and so on. And then we talked about another kind of structure that you might want to discover, where you don't just want to partition your examples into a discrete set of points, but you actually want hierarchical structure. And we explored an easy extension of k-means clustering to that problem of divisive clustering, where you start with your full data, you split it into clusters, and then you recursively split each of those clusters using k-means at each step along the way. All right, so we're reaching the end here, but I wanted to give you a brief tour of some really interesting recent developments using unsupervised learning. So it's worth saying that although supervised learning really kickstarted the recent machine learning explosion with deep learning approaches, much of the recent excitement in deep learning, certainly among researchers in deep learning, is in unsupervised spaces. And this is because there's a understanding that we're reaching the limitations of what we can do with kind of manually labeled examplers. So, you may know things like reCAPTCHA, the annoying thing you have to click through every time you want to fill out a form that says you're not a robot, which is essentially collecting free supervised training data for Google's algorithms. But there's a lot more that we can do if we can find ways to get away without all of those examples. So one approach that I think is really exciting is, so you may have heard about Fei Li, who released a data set called ImageNet, which is a very large supervised data set of images with labels of what is represented in the image. So it's like, this is a dog, this is a cat, this is a certain kind of bird, and so forth. So this has been kind of the engine of training vision models in deep learning. And it basically wasn't possible to do an unsupervised approach that would lead to similar performance on computer vision tasks until very recently, when unsupervised approaches have started becoming extremely popular. So this is an image of a particular paper that was looking at so-called contrastive unsupervised learning, which essentially tries to take images and find features for them. So basically find vectors and numbers for each image, such that these little augmentations, like this dog with these different operations that can be done on the same image, are all very close together and very far away from other images. So this is a totally unsupervised objective. It just requires a massive set of images with no labels. And it turns out that recently these have become competitive with the kinds of models you can learn from supervised learning on ImageNet. And then the second thing I wanted to highlight is that there are a couple other words that you may hear thrown around in discussions of machine learning. Words like self-supervised and semi-supervised. So I wanted to give you a sense of what these are, since unfortunately we don't have time to go sort of deeper down the line into other kinds of unsupervised approaches. So semi-supervised is perhaps the easiest to explain. It's also known as weakly supervised. So in this setting, you have a small number of labeled examples. So some pictures with actual labels that says this is a dog or this is a cat, but then you have a bunch of other data that isn't labeled. And the essential idea behind weakly supervised or semi-supervised learning is that you can get something out of the labels and then extend it to all this other data without labels. And that one of the interesting findings is that if you're clever about this, you can actually get a pretty long way with a pretty small number of labeled examples, and then allow the distribution of the rest of the data to take you the rest of the way. So this is exciting because it allows you to get away with labeling a lot less data when annotations are expensive. And then second, this idea of self-supervision is ways of turning unlabeled data into a supervised task. So basically, this has been particularly powerful in language modeling. The NLP group may be familiar with this. So these recent successes from OpenAI, like GPT-2, GPT-3, they're just trained on raw text from the web. So it's just all of the text that's written everywhere, all over the internet. So this isn't a supervised thing by itself. There's nothing saying, if you ask this question, here's the answer we want. If you, ask for a part of speech, this is the right part of speech. You just have raw text, but you can create a task where you say, okay, I want a model that takes in some previous context and predicts the next token. So in this example, you get the text, can you please come? And then you try to predict the word that comes after it. And this is actually a supervised problem because there's a ground truth answer in your data. There's an actual word that appears there, and in language modeling, this is essentially like a 100,000 way classification. So you're trying to predict over all of the tokens in your vocabulary what that next word is. So you can essentially use a lot of the techniques from supervised learning, but through this clever designing of ways that your data itself can provide supervision without any additional things. Yes, those are some exciting directions that I just wanted to share and get you a little excited about these directions. And I should close by saying that there have been a lot of influential thought leaders in AI recently that have been really making a strong case that these unsupervised methods, like the ones we've been talking about, are really the future of AI. So they're worth paying attention to.